Welcome to the presentation on comparators. Here we see the standard 741 op-amp or standard op-amp used as a comparator. If you notice, because of the large gain, that if it doesn't have negative feedback, we have no control over the gain and it will go to maximum. So no matter how small of a signal we put into the non-inverting side, it's going to go to the positive rail, which is some percentage of the power supply. If we put a minus in the non-inverting side, it's going to drive it to the minus power supply, some percentage of the maximum of the voltage input. Here we see an op-amp used as a comparator, and what we have is a +4 voltage going into the inverting side, and we have ground or 0 volts going into the non-inverting side. So the rule of the comparators is the largest input will drive it to that rail. Since we have 4 volts here and 0 volts here, 4 volts is greater than 0, so that would drive it to the minus rail, which 14 volts is pretty close to the 15 volt power supply. Here we have another example of an op-amp used as a comparator. We have +4 going into the non-inverting, 0 going into the inverting, 4 is greater than 0, so we're going to drive this to our positive rail. So +14 volts is pretty close to our 15 volt power supply. Here we have a little tricky comparator here where we are putting in minus voltages. Well, on the timeline or the number line, -5 is lower than -4, so -4 is greater, so we're going to drive this to the minus rail, which -14 volts is close to the -15. Here we see LM339, which is a actual comparator designed to be a comparator, and it has an open collector transistor inside of it. Okay, so we have our comparator, and this one will run between ground and 9 volts, and we have this open transistor where we need a pull-up resistor in order to get a high out of it. Okay, so when this goes on, it's actually pulling it to ground. Okay, so without this pull-up resistor, when we go high, we won't get a signal out. So it always needs some kind of a pull-up resistor. This is real good for relay coils and things like that, lights, because we can make this voltage anything. We could actually put 5 volts on this pull-up resistor and make it a logic device. Okay. Here we have two comparators put together as an inverting window comparator. So what we're looking for is an upper and lower trip point. And best way to test this is to go in between the two. So we have a upper limit of 4, lower limit of 3, so let's try 3.5. If I put 3.5 in here, 3.5 is greater than 4, it's going to go to the negative rail, which is low. Here we have 3.5, which 4 is greater than 3.5, so it's going to go to the minus rail. So between those 2 points, 3 and 4, we're going to go low. Everywhere else above and below of our trip points, it's going to be positive. Here we have another non-inverting window comparator based on the 339. And what we have here is voltage divider. Okay, so we have 2R and 1R. So if we have 3 into our 12, this guy's going to be 4 ohms. This guy's going to be 8 ohms. Okay, we're always concerned about what goes to the ground, not the other way around. So here, this one's going to be 4 volts. Okay, this guy, this voltage divider, we have 3R and R, so we have 4R into there, so we have 3 volts here, and we have 9 volts here, so we have +3 volts. Okay, because of the way this one works, we're going to go ahead and try in the middle again. So we got 3 and 4, so let's put 3.5 in. So 3.5, we're going to go ahead and 4 is greater. So this one's going to open up and we're going to use our pull-up resistor. 3.5 is greater than 3 volts, so we're going to go to the positive, which is going to open up the transistor and allow it to use the pull-up. So we're going to go high in between, and we're going to be low everywhere else, which is either lower than the lower trip point or higher than the upper trip point. Here we have our homework, and I'm going to give you hints on how to do these problems. I'm not going to do them for you, but I'm going to give you a good head start. First one is a standard comparator, and we have 10 volts, 7 volts, 10 volts going into the positive non-inverting side. So that means that 10 is greater than 7, so it's going to drive it to the positive rail, which is going to be about 9 volts, or simply positive rail. Here we have another comparator, 6 volts, and a voltage divider. Here's our formula for our voltage divider. But this one's very simple. This is just two equal size resistors, so it's a voltage divider exactly in half. So this one is going to be 4 volts on the input. And 4 volts is less than 6. 6 is going into the inverting side, excuse me. And so it's going to be driven to the negative rail. Here are problems 3 and 4. Again, we have a comparator, another voltage divider, and we're interested on what side the resistor that goes to ground. So 3 plus 6 is 9, so we just divide it into 9. So that's going to force this one to be 6 volts. Here we have 8 plus 4, that's a simple divider, into that. So this is going to be 4 volts, this is going to be 6 volts. 6 volts is greater than 4, so we're going to go to the minus rail. Here we have an AC signal put into our comparator, and we're comparing it to ground. So whenever this one input goes high, it's going to be greater than 1. It's a zero crossing comparator, so it's going to go to the max. Right at where it crosses again and goes minus, it's going to go low. Here are problems 5 and 6. Here we have a voltage divider, but it's based on a Zener diode. As you remember, if a Zener diode is forward biased, it acts like a diode, and it's like 0.6, 0.7 volts. If it's reverse bias, which this one is, it's going to be a Zener voltage, which is 4 volts. So we have 4 volts tied to ground, so this one's going to be set at 4. This one's going to be set at 7. So 7's greater than 4, so we're going to go to the positive rail. Here we have a stair-step function, and we are tied into another voltage divider. This is 9, split in half, so this is 4.5 volts. This is the input, so we're going to draw a line across here at 4.5 volts. And where it crosses, we're going to make a change. We just need to make that change and find out which direction it goes. So at 4.5 volts, greater than that, it's going to go to the minus rail. So it's going to go down here. If we're less than 4.5, we're going to go to the positive rail. If we're greater than 4.5, we're going to the negative. So less than, we're going to the positive, and greater than, we're going to go to the negative rail. Here's the last problem we have in another comparator, and we have a sine wave, 10 volts peak, and we have another voltage divider. 15 volts, 10 plus 5, 15, so we're going to have 5 volts here. So at the 5 volts, we're going to make a transition. We need to figure out what that transition is. So if this one is higher than the 5 volts, it's going to the positive rail. When this swings lower than 5, it's going to go to the negative rail.